Welcome to the deep dive. Today, we're jumping into something really fundamental, something that's everywhere, but maybe we don't always think about. Acids and bases. And we're going to look at how this little letter P actually unlocks a lot of understanding about them. I mean, just think about your own body.
Yeah.
Your blood pH, it's kept in this incredibly tight range, like 7.35 to 7.45. If it goes even slightly off, well, that causes some serious problems. It's kind of amazing, really.
It really is. And, it's not just biology. Anyone who's kept fish knows you've got to watch the water acidity, right? Or think industrially. Sulfuric acid is a huge one. Millions of tons made every year. Yeah, for fertilizers, steelmaking, all sorts of things. They're really fundamental chemicals.
Absolutely.
Yeah.
So the big question is, how do we actually get a handle on these compounds? How do we measure them, control them? That's our mission for this deep dive. Really pull back the curtain. We'll talk about what they are, how their strengths differ, and how we measure that strength. We'll connect it all, from your blood to lab reactions. Okay, let's get into it. So thinking way back, before all the fancy equipment, how did people first even identify acids and bases? Was it just like tasting things?
Well, yeah, believe it or not, tasting was a big part of it early on. Acids were known for that sour taste. Think vinegar, that's acetic acid. Or lemons, citric acid. Pecker up, right?
Bases.
Bases or alkalis, they tasted bitter. And they often feel slippery, kind of soapy, like a drain cleaner, though obviously don't taste that.
Right. Good safety tip.
Yeah.
So thankfully, we moved beyond taste test. What was the first sort of formal scientific idea?
The first big step was the Arrhenius theory. It's really the foundation. Arrhenius said an acid is something that when you dissolve it in water, it increases the concentration of hydronium ions, H3O plus X.
Okay, H3O plus L.
Got it. And a base. That's something that increases the hydroxide ion concentration, OH, in water. Simple examples, HCl, hydrochloric acid, and NaOH, sodium hydroxide.
That seems pretty clear, especially for water-based stuff. But were there gaps? Did it cover everything?
It was a great start, but yeah, it had limitations. It really only worked for reactions in water.
Ah.
And it only defined bases as things that directly produce hydroxide.
What about other substances that act like bases but don't have OH in their formula?
Good point. So what came next? How did the definition expand?
That's where Brønsted and Lowry came in. Their theory was a major leap forward. It's much more versatile.
And this one focuses on protons, right? H plus ions.
Exactly. It's all about proton transfer. A Brønsted-Lowry acid is a proton donor.
Donor, okay. And a Brønsted-Lowry base is a proton acceptor. It's about giving and taking that H plus pair out. And this leads to a really key idea. Conjugate acid-base pairs.
Conjugate pairs. Tell me more.
Okay, so when an acid donates its proton, what's left behind is called its conjugate base. And when a base accepts a proton, the new thing it forms is its conjugate acid. They always come in pairs.
Ah, I see. So like if HCl gives its proton to water?
Right. HCl is the acid. It gives the H plus to water. Water accepts it, becoming H3O plus. So H3O plus is the conjugate acid of water.
And the HCl is now just Cl.
Which is the conjugate base of HCl. Exactly. It's this dynamic exchange.
Okay, that makes sense. What about a base example, like ammonia, NH3?
Good one. Ammonia, NH3, doesn't have OH itself, but it acts as a base with water. NH3 accepts a proton from water, so NH3 is the base.
And it becomes NH4 plus mum?
Yep, ammonium ion, NH4 plus DOW, which is the conjugate acid of ammonia.
And the water, having lost a proton.
Becomes OH, hydroxide, its conjugate base. See how water can act as either an acid or a base here?
Yeah, I donated the proton that time, so it can swing both ways.
That's called being amphoteric. Water's a great example.
And just briefly, there's an even wider definition too, right? The Lewis theory.
That's right, Lewis theory. It broadens things even further by focusing on electron pairs. A Lewis acid accepts an electron pair, and a Lewis base donates an electron pair.
Okay.
It covers reactions that don't even involve protons. But for what we're diving into today, the Brønsted-Lowry view is often the most useful for typical aqueous solutions.
Got it. Okay, so we have these definitions, but we know some acids can, dissolve metal while others are in our food. Big difference in strength. What does strength actually mean chemically?
That's a crucial point, especially when you're first learning this stuff in, say, a fundamentals of chemistry course. Strength isn't just about danger levels, it's about dissociation. How much does the acid or base break apart or ionize when you put it in water?
Oh, okay. It's about breaking apart.
Exactly. So a strong acid, like HCl or sulfuric acid, basically ionizes completely, 100%. Every single molecule you put in water breaks apart and releases its proton to form H3O plus acid.
So if I have, say, 0.1 molar HCl.
You've got 0.1 molar H3O plus, essentially. For a monoproduct strong acid, one that gives one proton, the concentration of H3O plus is the same as the initial acid concentration. It's direct stoichiometry.
Okay, strong means complete breakup. What about weak ones then, like vinegar?
Right. Acetic acid in vinegar is a classic weak acid. Weak acids and weak bases, too, only partially ionize in water. Most of the molecules actually stay intact as the original molecule.
So they don't all break apart.
No, far from it. It sets up an equilibrium. The reaction goes both ways. HA plus H2O, H3O plus A. Molecules are constantly breaking apart and reforming.
Ah, equilibrium. That sounds important.
It's absolutely key, because for these weak ones, you cannot just assume the H3O plus concentration equals the initial concentration.
Right, because most of it hasn't actually released its proton.
Precisely. Simple stoichiometry doesn't work. We need another tool.
And this is where those equilibrium constants come in, Ka and Kb.
Exactly. This is where things get really interesting for weak acids and bases. Because it's an equilibrium, we use equilibrium constants to describe it. And specifically for acids, we use Ka, the acid dissociation constant. For bases, it's Kb, the base dissociation constant.
So Ka and Kb are just specific types of equilibrium constants, Kay?
That's right. If you understand how to write a general equilibrium constant expression, you understand Ka and Kb. It's the same principle. Products over reactants.
Okay, so they tell us how much dissociation actually happens, like a score.
That's a perfect way to think about it. For a weak acid, HA, its Ka expression, is the concentration of the products H3O plus and the conjugate base A multiplied together, divided by the concentration of the undissociated acid, HA. Ka equals H3O plus AHA.
And for a weak base B, it would be similar.
Yep. For B plus H2O, BH plus OH, the Kb equals BH plus OHB. These Ka and Kb values give us a precise number for the extent of dissociation. The larger the Ka value, the more it dissociates.
The stronger the weak acid.
Exactly. Same logic for Kb and weak bases.
Okay, so we can find these Chi and Kb values, but often they're like really tiny numbers with negative exponents, right? Like 10 to the minus 5 or 10 to the minus 10. Comparing 4.9 by 1010 for HCN versus, say, 1.8 by 10 to 5 for acetic acid. It's not immediately obvious which is stronger, just looking at those numbers. It feels awkward.
You've nailed the exact reason chemists came up with the P function. It makes these comparisons much, much easier. The P in chemistry basically means take the negative logarithm base 10 of.
Ah, negative log. So pK is just a log.
Precisely. pKa equals decilog. And similarly, pKb equals nest log.
And the magic is that this turns those tiny scientific notation numbers into, well, more normal positive numbers.
Exactly. It transforms numbers like 1.8 by 10 to 5 into something like 4.75, or 4.9 by 1010 becomes 9.31. Suddenly, they're much easier to look at and compare.
Okay, so pK and pKb make the numbers nicer. But how does it help compare strength? Is bigger pK stronger?
Here's the key thing to remember, and it can trip people up at first. It's an inverse relationship because of that negative sign in the logarithm.
No.
A smaller pK value means a larger K value.
Okay, wait. Smaller pK.
Larger Ka, which means a stronger acid.
Right. Smaller pK, stronger acid.
Got it. And the same logic applies for bases. A smaller pKb means a larger Kb, which means a stronger base.
Okay, that's the power of P. Now, we've mentioned water a lot. It seems pretty central. Does water itself do anything interesting chemically?
Oh, absolutely. Water isn't just a passive solvent. It actually undergoes self-ionization, also called autoionization. Two water molecules can react with each other, H2O plus H2O to H3O plus OH. One acts as an acid, the other as a base.
So water reacting with itself, that amphoteric thing again.
Exactly. And this equilibrium, though it lies far to the left, is incredibly important. It has its own equilibrium constant, the ion product constant for water, Kw. Kw equals H3O plus OH. And at 25 degrees Celsius, Kw always has the value 1.0 by 1014.
Right, 0.0 by 1014. That number seems familiar.
It's fundamental, and it leads to another beautiful connection for any conjugate acid-base pair. Their Ka multiplied by their Kb always equals Kw. So Ka, Kb equals Kw.
Wow. So if I know the Ka for an acid like HCN,
you can instantly calculate the Kb for its conjugate base, Cn, just by dividing Kw by Ka.
That's incredibly useful. Shows how linked everything is.
It really is. And this constant concentration product, Kw, is the basis for the most famous scale of all.
The pH scale. Finally.
The pH scale. It's just another application of that P function, pH H3O plus set. It's simply the negative log of the hydronium ion concentration.
There's POH too, right?
Yep, POH equals dash log OH. And because H3O plus times OH always equals KW, 1014 at 25 degrees C, if you take the negative log of that whole equation.
It's pH plus POH equals 14.
Exactly.
Yeah.
pH plus POH equals 14.00 at 25 degrees C. So knowing one tells you the other immediately.
So pH less than 7 is acidic. pH greater than 7 is basic.
That's the standard definition.
And going back to blood, pH 7.35 to 7.45. That's slightly basic, just a tiny bit, but critical.
Absolutely critical. And calculating pH is different for strong versus weak, remember?
Right. Strong acid, like 0.05 MHCl. pH is just Nash log 0.05.
Yep, which is about 1.3 U. Direct calculation because it fully dissociates. Same idea for a strong base, like 0.05 M and NaOH. Find POH first, then pH.
But for a weak acid, say 0.05 M acetic acid, I can't just use 0.05.
No, you absolutely cannot. You have to use its chi value and the equilibrium expression, or an approximation like the ICE table method, to figure out the actual H3O plus at equilibrium first, then take the negative log for pH.
Makes sense. You need the equilibrium concentration,
which will be much lower than the initial concentration.
Okay, we've seen how sensitive pH can be. That blood example really drives it home. So how does blood, or how do chemists in labs, keep pH stable when things are added? What's the trick?
The trick is using buffer solutions. They are truly remarkable chemical systems.
Buffers. I've heard that term. What are they exactly?
A buffer is typically a solution that contains significant amounts of both a weak acid A and B, its conjugate base.
Ah, the conjugate pair again?
Yes. Or you could have a weak base and its conjugate acid. The key is having both members of the conjugate pair present together.
Like acetic acid mixed with sodium acetate. The acetate ion is the conjugate base.
Perfect example. Or ammonia mixed with ammonium chloride. NH3 is the weak base. NH4 plus is its conjugate acid.
So how does having both parts stop the pH from changing much? What's the mechanism?
It's quite clever. Think about the acetic acid-acetate buffer. If you add a little bit of strong acid, which adds H3O+, the acetate ions, the conjugate base component in the buffer, will react with that added H3O+ ETH away, effectively neutralizing it and turning it back into acetic acid and water.
So the base part of the buffer soaks up the added acid.
Exactly. And if you add a little bit of strong base, which adds OH,
the weak acid part reacts.
Right. The acetic acid molecules donate their protons to the added OH, neutralizing it and forming water and acetate ions.
So either way, the added H3O plus or OH gets consumed by one part of the buffer pair, preventing a large swing in the overall pH.
That's the essence of it. They act like sponges for added acid or base, keeping the pH remarkably stable.
That is clever. And is there a way to calculate the pH of a buffer easily?
There is. Using the Henderson-Hasselbalch equation, it's a very handy tool for buffer calculations.
Henderson-Hasselbalch. Okay, what does it say?
It relates the pH of the buffer directly to the pKa of the weak acid component and the ratio of the concentrations of the conjugate base and the weak acid. The equation is pH pK plus log conjugate base weak acid.
pH Pa plus log of the base acid ratio.
Okay, so if you know the pKa of your weak acid and the concentrations of the acid in its conjugate base, you can calculate the buffer's pH.
And you could use it the other way too, right? To design a buffer for a specific pH.
Absolutely. Let's say you need a buffer around pH 5. You'd ideally choose a weak acid with a pK close to 5, like acetic acid, pK at 4.75. Then you adjust the ratio of acid to acetic acid until the log term gives you the small adjustment needed to hit your target pH precisely.
And if the concentrations of the acid and base forms are equal?
If conjugate base equals weak acid, then the ratio is 1. The log of 1 is 0.
So pH just equals pKa.
Exactly. That's the point where a buffer has its maximum capacity to resist changes in either direction. And this whole buffer concept is how your blood maintains that vital narrow pH range. It relies on systems like the carbonic acid bicarbonate buffer.
Amazing stuff. Okay, so we understand acids, bases, strength, pKa, pH, buffers. What about actually measuring quantities? Like how much acid is in this unknown sample?
Right. Moving from understanding to quantifying. This brings us to neutralization reactions and the technique of titration.
Neutralization. That sounds like acid meets base and they cancel out.
Essentially, yes. It's a chemical reaction where an acid and a base react, typically forming a salt and water, like HCl plus NaOH plus H2O. The crucial part is that they react in precise stoichiometric ratios based on the balanced chemical equation.
Stoichiometry, again, those mole ratios.
Exactly. If you know the stoichiometry, like it's a 1.1 reaction, then you know that at the point of complete neutralization, the moles of acid initially present equal the moles of base added, or vice versa. We often use the formula 1A acid acid equals 1B CV base, where A and B are the coefficients from the balanced equation, C is concentration, and V is volume.
So you can calculate exactly how much of one you need to react with the other. If I have 25 millimole of 0.5 millim HDl, I can figure out the volume of, say, zero point 0.1 millim NaOH needed to neutralize it.
Precisely. And the lab technique we use to do this carefully is called titration.
Titration. Okay, how does that work in practice?
Titration is a method to find the unknown concentration of a solution, the analyte, by carefully adding a solution of known concentration, the titrant, until the reaction between them is just complete.
So you're adding the known stuff bit by bit until something happens.
Until you reach the equivalence point. That's the theoretical point, where the amount of titrant added is stoichiometrically exactly enough to react with all of the analyte initially present. Moles equal moles, according to the balanced equation.
The equivalence point. How do you know when you've hit it? You can't see the moles reacting.
Good question. You need some way to detect it. There are two main approaches. One is using a visual indicator. This is a chemical dye that changes color very sharply at a specific pH.
Like litmus paper, but maybe more precise.
Kind of, yeah. You add a couple of drops to your analyte solution. You choose an indicator whose color change pH range brackets the pH you expect at the equivalence point. The point where the color changes is called the endpoint.
Endpoint. So you want the endpoint color change to be really close to the equivalence point. Moles are equal.
Ideally, yes. You select the indicator carefully for that. A good indicator has a peak in value, similar to pH, but for indicators, close to the expected pH at equivalence. The other method is instrumental, using a pH meter.
Tracking the pH directly.
Right. You measure the pH as you add the titrant and plot a graph of pH versus volume added. The equivalence point shows up as the point of steepest slope on that curve. Very precise.
Now, is the pH at the equivalence point always 7, like neutral?
That's a common misconception. It's only pH 7 if you're titrating a strong acid with a strong base.
Oh, why not always?
Think about titrating a weak acid with a strong base. At the equivalence point, all the weak acid has been converted into its conjugate base.
And weak bases make the solution slightly basic.
Exactly. So the pH at the equivalence point for a weak acid-strong base titration will be greater than 7.
And I guess for a weak base-strong acid titration, it would be less than 7.
Precisely. The conjugate acid formed makes the solution slightly acidic. Understanding this is crucial for choosing the right indicator.
Wow, okay. We have covered a lot of ground today, a real deep dive into acids and bases. We went from the basic definitions, Arrhenius, Brunstad-Lowry, explored strength, K, KB.
And then unlocked that comparison power with PK and PKB, the P function making life easier.
Yeah, then connecting it all to water, KOBU, the pH scale we see everywhere.
And those brilliant buffer systems that maintain stability, like in our blood. Finishing with how we actually measure things precisely with neutralization and titration.
You listening really do have a shortcut now to being well-informed on all this essential chemistry.
Yeah, these concepts, they really are central to understanding so much chemistry and biology.
Yeah.
How reactions happen, how systems stay balanced.
Definitely. So here's a final thought to maybe mull over. The next time you face some challenge in life that needs, balance and precision, maybe it's your diet, maybe an environmental issue, maybe just a tricky problem at work, how could thinking like a chemist about buffering or equilibrium maybe help you find a more stable, more effective approach? Something to think about.